Good morning, everyone. Welcome to lecture number 26. So, in the last lecture, we were implementing disjoint union data structure using linked list. We saw one improvisation, which was basically rank-based, rank or size of the list. So, all we did is, so this picture pretty much summarizes what we did. So, we keep track of size of the set at the header for the linked list. And in the union, while doing the union, so we'll always ensure that the smaller set is appended to the end of the linked list. Okay, so that the number of updates is done to the elements of the smaller set. So we did analysis. So we saw that total of n union operations are allowed. So together they will take order of n log n time. Okay. So I'll just quickly go over the argument. So the argument was, so the intuitive idea was essentially the worst possibility for the union to make largest possible comparisons as keeping both the sets of the same size. Okay, so that's the essential intuition, which basically works well. So for formality, so we counted the number of updates to an element. Okay, so we just put a watch on each of the element, see how many updates are possible at most. So we proved that at most order of log n updates are possible for each element, and hence giving us this bound. So total there are n elements, so n log n updates total up to a constant factor. Okay, so for this, the simple observation is the following. So we wrote it as a claim. If any element x, if it has seen k updates, then there is a minimum guarantee on the set in which it is contained in. Okay, suppose x is contained in Sx, then we can say that if x has seen k updates so far, then size of Sx must be at least 2 power k. Now this proves the required result because maximum possible size of the set is n. So hence any element can see at most order of log n many updates. In fact, log n many updates, not more than that, because size of the set cannot go beyond n. Okay, so this was a short inductive argument. So all we did was, I'll just go over the induction again. That's all, because yesterday I didn't have much space here. So yeah. So base case I hope is clear. I will not go over the base case again. Okay. So the base case was fairly trivial when k equal to 1. For the induction, sorry. So we assume that, so induction hypothesis, suppose the statement is true for k for up to k minus 1 updates. So consider the kth update. For x. Okay. Let Sx be the set containing x, and Sy be such that Sx union Sy has caused the kth update. To x. Okay. Now, so far x has seen k minus 1 updates. So by induction hypothesis, What is the cardinality of Sx? So look at the claim. Claim says if X has seen k updates so far, the set containing it must have at least 2 power k elements. So here the set containing it, that is Sx, should have at least 2 power k minus 1 elements. Okay. Now, so since update is being made to X, so since X is being updated for this union, it must be that cardinality of Sx is smaller than or equal to cardinality of Sy, right? Else we would not have updated. See, when I say X is being updated, the way we are implementing it, all elements of Sx are being updated. When does it happen? That's only when size of the set Sx is smaller than size of Sy. Okay. But we know that Sx is at least power k minus 1. So therefore, Sy is also at least 2 power k minus 1. Now, because they are disjoint sets, cardinality of Sx union Sy is cardinality of Sx plus cardinality of Sy, which by induction hypothesis, the first one is at least 2 power k minus 1. And for the reason that X is being updated, it has to be that Sy has larger cardinality. So this is at least 2 into 2 power k minus 1, which is 2 power k. Now, Sx union Sy is the new set containing X. So this is the new set containing X. So therefore, this completes the proof. That is all we needed, right? The set containing X after X has seen k updates is at least it has at least 2 power k elements, and that's what we have proved here. Okay. Yeah. Okay. Yeah. So this basically gives us the required result. So this is a significant improvement compared to the previous implementation, the original implementation. So we'll see effect on crystals soon. So just to summarize, make set, there is no change. Each make set operation will take order of 1 time. Find, there is no change. Each operation will take order 1 time. Union, in total, it's n log n time. So if there are m operations, then together the overall time will be order of m plus n log n time. Okay, so that is so effect on Kruskal's. So Kruskal's has, it does sort the edges, which is m log m. Sorry. And union, together they will contribute n log n plus. Now find operation, like we saw in the last lecture, find, there could be order of m finds, right? You will have to search. So the final edge being added to the tree could be the last edge in the sorted list. So that will take order of n. And assuming that m is greater or equal to n, this order of n make set is also subsumed. So this is the complexity for Kruskal. So it's essentially, if you assume the graph has at least n edges, then this is order of m log n. If in fact log n and log m are the same asymptotically, so I can as well write this as log n, m log n, if m is greater than or equal to n. This is a significant improvement compared to the naive implementation where we had order of mn time, or the original implementation where there was order of n square 2. Okay, so okay, yeah, I'll pause for a minute to take questions.
Hello.
Yes.
Sir, can we quickly go over the Kruskal's algorithm using this disjoint sets, because I'm just a bit doubt regarding the find.
Okay. So how is, so let's just write down Kruskal's. So step one, sort edges so that weight of E1 less than or equal to weight of E2 less than or equal to etc. weight of EM. Okay. Second step, so set IS empty set. Third step, while loop. So let's fill it later. Fourth step, if I union EI, yeah, we don't need I. So for I equal to 1 to M, do is acyclic, then set IS I union EI. Okay. You can also keep track of the cardinality. So output I. This is one simple version. You can also have checks in between. If once you know that you have n minus n edges, you can just output. Yeah. Now, what was exactly your doubt?
So my question was, how are we like making use of disjoint sets in this algo?
Okay.
Like we are starting with each vertex in a different set using make set, and then unioning, like making them union
Yeah.
with
So
the
you just
condition that
take, so the, yeah, I'll do that. So initially you do n make set operations. Okay. So this is it. So let's say first edges E1 is say 1, 5. Okay. So then you'll call union. So you'll do first find 1, 5, then union 1, 5. Let's say E2 is 3, 4. Then you'll do union 3, 4. So third edge is, let's say E3 is E4 it was, let's say 1, 4. Then you'll do union 1, 4. Okay. So the sets will look like, so initially it was 1, 5. So you have 1, 5 as the set. The remaining sets remain the same. And the next iteration, you'll have 1, 5, 3, 4. The next iteration, you'll have, so this edge is between 1 and 4, right? So it will be 1, 5, 3, 4, and so on. This is how it will look like. So each of them, there will be find, corresponding find. So you'll have to find the set, right? So this will also have find 1, find 5. This again, find. I mean, the union will call for find. Union will call for find 4. Again, find 1, find 4. Yeah.
So I was asking, when if there is an edge 1, 3, then it will be simply discarded by union. Is it?
Yes. So the find immediately finds it, right? So if you have, say, yeah, at this, say, E5 is, let's change the color. Say E5 is, so E5 is 1, 5. Okay, 1, 5 is already included. So yeah, 1, 3, let's say. So the find sees that both the sets are the same, right? Then you know that there is a cycle. So find one. Find one is equal to find 3 implies cycle. That is all.
And in the last, we output the maximum cardinality set. Is it?
No, what is maximum cardinality set? Output I, that is it. See, if I cardinality of I is n minus 1, that is it. The best way is you just run through 1 to m. As long as you can add without any cycle, that's it. So you can terminate early if the cardinality of I is n minus 1, assuming the graph is connected.
Sir, okay. And my question was,
Mm-hmm.
we are dealing with disjoint sets, right?
Yeah. So what was the question?
So initially we have n disjoint sets, and we are converging to a lesser number of sets.
Yes.
So like I'm not able to get what is the output here, because we don't have any edges relation here in these sets. We have to give this minimum
Oh,
span.
so what you want is okay. So that is a good point. So you need to keep track of the tree, right? See,
Yes.
no. I has tree, right? I has edges. You're keeping track of edges itself. See, okay. I understood what you're saying. Okay, so the set data structure just keeps track of the connected components. Okay, vertices in the connected components, but the set I has all the edges. So you need to keep track of the edges that you have chosen. That's what your question, right? Where is the tree?
Yes.
Is that right?
Yes.
Yeah. So yeah, you'll have to keep track of the edges in I itself. Okay, but only thing that union data structure does is it helps finding cycle if it exists fairly simply without doing anything. Okay, so just see if both are in the same set or not. So this structure is additional. It just helps us finding the cycle fairly quickly. That's it. If there is a cycle, and
Yes, sir.
keeping track of the edges, you do it here. So that is it. So yeah, you need to know which edges you have chosen. Otherwise, you will not know the tree. That's true. That's a good point. Yeah.
Okay. So we are making the sets union because we are accounting for the edge that is added in I.
Yeah.
Okay, sir. Thank you. It was clear now.
Yeah. So the only problem is checking for cycle. That is what we are implementing with this set. Whatever.
So, sir, the step 4 of the algorithm, that's a separate union, different from this union of operation that you have listed here, because there we are taking a union of edges.
Where? No, this one. Oh, no, this is different. No, this is different. So see, the whole business here is only to check for cycle. Okay. So this we need to keep track of for the edges, right? I mean, to get the tree finally. So I is the tree. Okay. I is the tree. There is no change for this. So only part we are doing here is implementing this. So this was the hard part, right? So to improve this, so we implement this using our, what is that? Disjoint union or union find. It's also called union find data structure, which is done independently this way.
Okay, sir. And sir, can you go back to the last slide?
This one? Or one slide
where you wrote the time complexity. Last one.
This one or this one, right? Is it? Can you see it?
Yes, this one.
This one. Yeah.
Yeah, so here, how are we able to write m log n? It should be m log m, right? Because if m is greater than n,
yeah, so
log m would be greater than log n.
What is m, right? M can be at most n choose 2, right? So log n and log m asymptotically will be the same, right? Up to a constant factor.
Okay.
So log of n choose 2 will be 2 log n. So yeah.
Yeah.
Okay. Yeah. Any questions about the implementation or about the proof?
Sir,
Yes.
just a clarification, like here we are keeping the track of all the edges first, like every edge, single edge, and when we are forming a tree, then we also keep the track of the trees, and if there is an edge connecting trees, then we will also doing the union of both the trees.
Yeah, see, tree you can just imagine as collection of edges, right? It's basically a subgraph.
Yeah.
Okay. So
Yeah.
yeah,
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 so
go ahead.
I was saying that later in the algorithm, we are also keeping track of the trees so that if there any edge that between the trees that we have already created, then we will union them also, right?
Yeah, see, this set I, right, that is being kept as it is. This is a collection of edges. Okay. So
Okay.
the whole thing with this disjoint set that we did, right, disjoint set or disjoint union operation, it's basically to check for acyclicity. So this is completely separate. Okay, so this is this implementation part. So to check this, we need to keep track of this. So first, so I mean, if you want to write, if you have to write the code, you'll have to write, okay, so make whatever, make one, etc., make n. Okay, and then so here what you do is, so you do union find. Okay, so union, say ei is, let's say ei is ui vi. Okay, so then what you do is you find ui, find vi. If find ui is equal to find vi, then you know that this cannot be added, so discard and go to the next iteration. So if find ui is not equal to find vi, then do union ui vi. Okay, so that has to be there. So that part is hidden here, that we didn't write. Okay, so that's
Yeah.
what we have implemented here. Yeah.
Yes.
Yeah. Okay, maybe it's a good exercise to write the full code. Okay, so I'll leave it as an exercise for you to write the full pseudocode. You don't have to write a C program. So yeah. So those who are doing advanced programming, so do you implement any greedy algorithm? No. I believe most of the, all of the MTechs are doing, and many of the scholars are also doing, I believe. So have you implemented any of the greedy algorithms so far?
Yes, sir. We have.
What was it?
It was like a bin packing problem, variation of bin packing problem.
Bin packing. Okay. So then, okay, for bin packing, you may need priority queues and so on. Or no?
Yes, sir.
You needed. So you had to implement priority queues, is it?
Yeah, but most of us did via maps. So
Okay. Yeah. Yeah. So if this were the implementation question there, I mean, then you'll have to implement both of this. So yeah, it's worth writing a pseudocode at least. Okay. So if not the full C code. Okay. If there are no questions, so in the next 20-25 minutes, we are going to see another improvisation, but without much details. I'll just give one example from the textbook and then leave the analysis. The analysis bit more involved, and we'll move to the next data structure, which is going to be heap. Okay. Okay. So here, in fact, the improvement is fairly good. I mean, we cannot hope for any further improvement here, right? If you look at this, it's not really for cruscals, right? Even if you improve the union, say what is it we can hope to improve? See, these are the best possible, right? Make, set, and find, order one time. One thing is you can possibly hope for improvement in union. Maybe ideally would have had allowed to have this as order n. Okay. But for Kruskal's, there is already a bottleneck sorting the edges, m log m, right? So you cannot really improve Kruskal's further. So this is the best possible for Kruskal, unless you don't want to sort. Okay, so then the algorithm completely changes. Okay, so yeah, but just for the sake of it, I mean, it could be that other applications. See, other applications, this is the bottleneck, right? In other applications, if you have m operations, and you know that because the sets are disjoint, there can be at most n-1 of union operations among these m operations. The remaining must be find as well as make set. So you could try to improve, because this is going to be the bottleneck there, this log n factor. Okay. So it turns out the improvement, you can say, let's go back to the implementation. What was the implementation? We used linked list, right? So what is the next data structure that you have seen? I mean, when studying linked list, what is the data structure soon after that you would have seen? So you can imagine linked lists are being linear, right? Like you just draw a line. What are the structures which are not linear but still represent links?
Tree.
Tree, right? So where there is a natural branching. So in fact, linked lists are trees which are simple paths. Okay. So when you have branches, then you have non-trivial trees. Okay. So the idea is to use forests. In fact, I mean, by forest, I mean each set is stored as a tree. Okay. So instead of storing a set as a linked list, store each set as a tree. Okay. So, I mean, if we want to improve our performance of union operation, that is a natural next step, right? I mean, okay, you have linked list. Then, so what is the bottleneck there? To update the pointer, you will have to traverse the linked list completely. If you have tree, maybe you can just update the root. That's it, right? That's the intuition, right? So, yeah. So the idea is to store each set as a tree. Okay. Now the parent pointer actually means parent in the tree. Okay. So that is a modification. So we'll see a simple example here. So say set 1 is CHEB. This is from CLRS book. Okay. So then you could represent it as this tree. I mean, you might question, okay, why this tree? Could be other ways of representing trees. Yes, you could have represented it as B hanging from here. So anything. I'm just giving an example. That's all. Okay. So, and of course, the performance will depend on the shape of the tree. The second is just a linked list again. So you have this tree, which is like a path FD. Okay. Now, yeah. So let's just look at implementing operations in this. Okay. And then see, can we get a performance improvement? So quickly, see, make set is no difficult, right? So make set, we are having the same protocol. Okay. So you're doing n make sets at the beginning. So which is basically trees with one node, which is no different from making a linked list, right? With one node. They're essentially the same. So it's order one operation. Okay. So that is something is under the carpet. Now let's look at find. So how will you do find operation? So let's say I want to do find B. So what is the purpose of find? We need to find the set which it belongs to. So what is the set here? It is a root of the tree. Okay. So each tree we represent it by the root. So these are rooted trees. So this is root here. This is root here. Okay. Now if I want to find B, how will I do? I need to find the root of the tree where B belongs to, right? So I take the element B. See, it's the same way. So the elements are stored in an array. So when I know B, I can access the pointer, parent pointer of B in one operation. then I go to the parent, and I go to the parent, and so the nomenclature that CLRS follows is the root will point to itself, so that you'll distinguish from other nodes. Okay, so if you see the parent pointer pointing to itself, then you know that this is the root. So you output C as a parent. So if you were to find G, you'll start from G, go upwards. When you hit the root, you know that you have found the root of the tree containing G. It could be that this tree is just ending here only. So then you'll just report B as the tree. Okay. So the only parameter that is interesting here is the height of the tree, right? So height of the tree is an important factor. So find B will require height many operations. I mean, asymptotically, what I mean is, it depends on how do you access and so on, but order of height many operations. Okay. See, there is a lot of arbitrariness here. First of all, you don't know what is a height. Okay, so height is a parameter now. So for the the change compared to linked list representation, everybody will be pointing to the set containing it. Okay, so find was trivial. You just go access the parent pointer. That's it. That gives you the set. Whereas in the tree representation, that is not the case. You would not know if I get B or H, I would not know what is the set containing it, what is the root. So I'll have to traverse upwards till I hit the root. Okay, so that is a non-triviality. Now, can anybody tell me about union? How would you do union? Say I want to do union of these two sets. How will you do it?
Update the parent pointer, update the root to point to the root of other tree.
Yeah, so if we don't have constraint that it's a binary tree or whatever, number of children is not limited. So the best way is to do union is take one of them, make it to point to the root of the other one. Okay. See, in the linked list, what we did is we appended it at the end. So here what we do is we just update it here. Then you don't have to change anything else, right? So this is for union.
Sir, but again, there is this point of height, right?
Yeah. Modulo that, yes. Height can increase arbitrarily and so on. So there are some cleverer things that we can do about it. But right now, this is the simplest way. Okay, so maybe we'll, so this is the English description of. So if T1 and T2 are the trees representing sets S1 and S2, then all we do is attach the root of T2 as a child of root of T1. It could be cleverer. You can count like we did in the case of linked list implementation. You can count the number of elements and attach to the tree which has a larger number of elements, or you can also count the height and attach to a tree with the larger height. Okay, so T1 will be larger height. So those things, those improvisations or heuristics can always be done, but without any of that, it just simply is this. So this is again a better depiction. Okay, you just attach C to the root of the second tree, which is F here. Okay, this is how it looks like. Okay, so this is what we have just mentioned. So for find, you'll have to start navigating from the node until you hit the root. Okay, so output the root node. Yeah, so for example, in this, if you start with E, you'll have to go to C and then go to F, then output. If you start with, say, B, go to H, go to C, go to F. So like I said before, the height matters here. Okay. Let me just summarize the complexity. So make no difference. You're just making a tree with one node, which is order one operation. You have to create one pointer or one structure variable. Union now, what is the cost of union? Here. So assuming that you have found the roots, right? So if you found the roots, then the union is basically updating one pointer. That's it, right? Yeah. Somebody wanted to speak?
Hello.
Yes.
Sir, can we make this update in this tree? Like each node can contain a representative of the tree, that is the root, as a like parent, like
No,
representative.
that could be, yeah, that could be one improvisation. Yeah. I mean, I'm just discussing the naive one, and I will also suggest one improvisation which actually gives you a drastic improvement.
Okay.
This one, yeah, this one. See, the problem with this idea is you will have the trouble of. So when you do union, right, you'll have to update the whole tree. Okay, that is something that we wanted to avoid, right? So in the linked list implementation, you'll have to update the parent pointer of every element in the smaller set, right?
Can't we
So if
make
you,
only the roots, the smaller sets roots to the like while union, the smaller sets
yeah,
root only if we change, we'll come to that root and then we just update f. Okay, it won't work. It won't work. Okay, sir. Sorry, sir.
yeah, what I mean is, the cost will be more, at least
Yes,
for
sir.
union. Okay,
Yes,
it might
yes.
save find. Okay, so it might save on find, but for union the cost will be more. So here,
Okay.
assuming that you have found the roots, then the cost of union is just order 1. Okay, so the only bottleneck here in this implementation is a find operation, where each find can require as much as the height of the tree. Okay, so this is the non-trivial part. Now, what is a bound on the height of the tree? In the worst case, it will look like a path, right? Just like in this example. In the worst case, it can look like a path. The height, I mean, it is possible that the tree is just a path. In that case, we didn't save anything, right? Yeah. So, I mean, overall, our time complexity could be empty, where t is the bad height, which is order n, when you have a path. Okay. So what I wanted to say is, if you don't make any adjustments or make any, say, clever, any extra information, or if you don't use any extra information, the naive implementation is as bad as the linked list implementation. There's nothing, no gain. But what if we do the same trick as before? At the root, you just maintain the number of nodes information. So I'll say this has size 4, this has size 3. Okay. So now if I don't want to, okay, so both has, okay, not size, height, sorry. Size doesn't matter. So height. So this has height 3, this has height 3. So in this case, it doesn't matter which way you do. The height is not, height is going to increase no matter what. But I'll give another example. I'll just modify this same thing. Okay. So let's consider this. Now, the first tree has height 3. The second one has height 2. I'm just measuring this as height 2. Okay, so I don't know, in many of the books you might have had this as height 1. Was it or height 2? Okay, I hope I'm clear, right? See, in many, so for example, I mean, in my literature, this will be depth 1. Okay, so depth is a different word for height. So whereas I have taken this as height 2 and height 3. I hope everybody is fine with it. So I'm also counting this. Yeah. So yeah, a single node is a tree of height 1. I think in some literature it is height 0. Okay. So, but yeah, that should not alter what we are doing. Okay. Yeah. So here you have height 3 and height 2. So what you do is you attach this one to the root of the other. That is here. Okay. So then the height did not change, right? Height is 3. Whereas if I had performed the other way around, the height would have been 4. Height would have increased. Okay. So this is one heuristic or one improvisation. Okay. So with this, we can argue in a similar fashion to what we did with the linked list. We can argue that the height of the resulting tree is always order log n. You cannot blow up because the number of nodes will double, right? Roughly. If the height, so I mean, intuitively it's the same argument. So you can argue that height of the resulting tree is order log n. So therefore, total time that is required for m find operations will be m log n. Okay, so assuming there are m find operations. So we didn't save much. I mean, it's the same as linked list implementation. There it was union was n log n. So here it is m log n. So in a way worse than union. I mean, worse than our linked list implementation, because here find is the one troublemaker, whereas there it was a union. Okay, now number of find operations m could be arbitrarily bigger than n. Though in the case of Kruskal's it was n choose 2, the maximum possible value. Okay. Yeah, so I'm not.
The resulting tree, are you meaning it is after the resulting tree after union operation?
Yeah. So I mean, resulting trees. What I mean is, at any point of time, if say n is the number of elements it's holding, you can ensure that the tree has size. I mean, height order of log n with this kind of union. So if you do union this way, say you have sequence of union operations which builds a set, right? And if you consider the corresponding trees, the height will be maintained as order log n. It won't go beyond. Okay.
Okay.
Yeah. Okay. So this I leave it as an exercise. So reference is CLRS, but I'm going to suggest an further improvement again without analysis. I'll just tell you what it is. Okay. So instead of maintaining maintaining heights at each of the roots, okay, what we do is we maintain height, that is, so upper bound on the height, okay, on the, so what we do is for each node we'll maintain an upper bound on the height, that is called as rank. Okay. So let's see. So here, if you take this example, so this has height 1, this has height 2, this has height 1, this has height 3, this has height 1, and so on. So here height 1, height 2, height 1, height 1, height 2. Okay. So for every node, we'll maintain this height information. Okay. Now, so what, does it affect the union? When you do union, will you have to update the height of everything? Just like updating the pointers in the set linked list implementation, right? You don't have to, right? Because when I do union, if I attach this as a subtree here, the height of this subtree does not change. So this rank information does not change here. Rank information does not change. In the worst case, rank information of the root node might change. When will it change? The previous example. When the heights are the same. When the heights are the same, now the height information for the root will become 4. Everybody else, it will be the same. 3, 2, 1, 1, 2, 1. Okay. So again, there is only one update that is required, that is at the root. Okay. So this extra information, it really does not change much in the union implementation. It only affects the count at the or rank at the root of the resulting tree. So only one information needs to be updated. Okay, sorry, I have to go back again. Okay, so this again height. Okay, I'm sorry. But this alone does not save us anything. But there is a second heuristic, which is called path compression, which is also simple, but that is the most effective one. Okay, so I'll demonstrate using the example in CLRS. Say you are doing a find operation. Okay, so find A. So how will it happen? So you start traversing from A till you hit root. Say F is the root. So this is the root. Okay. So the path compression is when you do this find, what you do is you just detach all of this, you dismantle this portion of the tree, you attach all these nodes, all these subtrees here to the root. This is the compression. Okay. So when you traverse, you look at the rooted subtrees. So all of them, so what you do is this kind of jumping. Okay. This points now, this points to root now, this points to root now, and so on. This already was. Okay. This looks like a crazy idea, right? It might also look to many of you that okay, maybe hard to implement. It's not very hard to implement because while you traverse, right, parent, 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 if you just see, okay, A dot parent. If A dot parent is not equal to A, what I do is I just take this, so I'll make this point to the one above. Okay, so sorry, what is that? Okay, so I'll just keep that information. So I'll just keep on traversing. While traversing, so I need to ensure that these are all pointed upwards. So I need to kind of store these values and update the pointers to wherever I end up. That is f dot parent is equal to f. So that is where I stop. Okay, but let's not worry about implementation issues. But at least is the idea clear to everyone?
So for every find operation, are we doing this?
Exactly.
Then,
so whenever you have a find operation, if if the element being I mean your finding is not immediate descendant of the root, so then you'll have a path. So along the path you just do this compression. You just attach it to the root. So for example, if I okay, so let me see if I have a blank page. So for example, if you have this as the tree. It may not be binary, okay? So if you do find here, right? So the result of that find will be that this pointer will point to root, this pointer will point to root. Okay. Now if you find here, so your next find is here. Let's say result of that find will be this pointer will be to root and this pointer will be to root, and so on. So whole of this thing is thrown away. Okay. So it could be that yeah, I mean tree is not binary. That's fine. Okay. Yeah, it will. I mean, each find will mess up the tree structure. Okay, it will. But what does it do? I mean, if your find was to a large height, right? That is, find was costing you much. Next time, find for the same element will be costing much less. That is a kind of intuition, right? Okay. Yeah. Okay. So, I mean, I'm not going to prove any statement here. I'll just state the result. It's fairly complicated to prove this. Okay. Yeah. So with the above improvisation, if you are having m find operations, you can show that it can be done in this time. There's a weird number sitting there, weird function sitting there, m log star n. Okay. So where this log star n is defined as follows. Okay. So this is the smallest I such that 2 power 2 power 2 power 2 power 2 power I times is greater than or equal to n. Okay, this is an ultra slow growing function log star n. This is not basically log n. Okay, so for example, if it is n is 100, so 2 power 2 is 4, right? 2 power 2 power 2, so 2 to the power 4, it is 16. 2 power 2 power 2 power 2, what is that? 2 power 2, it's 4, 2 to 4, 16, 2 power 16, right? So when equal to 100, this number log star n is 4. Okay, so it's the same even when n is 1000, even when n is 2 power 16 is more than 10,000, I guess so, right? Yeah. So even when it's 10,000, it's the same. Okay, so now you can see that it is slow growing, right? So you just tower up powers of 2 and see the number of times you have to tower up so that you'll cross n. That is a number. Okay, so even when n is 1 million, so log star n will be something like 6. Okay, so very super slow growing function. So there is also another name for this. This is called inverse Ackermann function. Not exactly the same as what I have defined, but slightly bit more complicated looking, but essentially the same growth as this function. Okay, what you can imagine is for all practical purposes, this factor is like a constant. Even when n is 1 billion, this is going to be constant. So the improvement happens to be very drastic. You essentially have gotten rid of that log n factor to something very slow growing with respect to n. Okay. Yeah. So I'll leave the analysis. Like I said, it's fairly involved, and we'll need at least a couple of lectures to do it. We'll skip it for now because we are fairly slower than what I had planned. So yeah, all of these results, this forest implementation is given in section 21.2, and section 21.3 gives this proof of this theorem in this book. Okay, so I leave it as a reading exercise. Whenever I say reading exercise, it's not part of the syllabus, but you can read it for fun. Okay. Okay. Good. So I think yeah, I'll stop here for today. It's already 8:55. So Raghav, please stop the recording. Those who have